This is part 2 of section 1.4. Continuing on, we would like to look at this graph and determine the intervals on which it is increasing, decreasing, constant, and to identify any local relative maximum or minima and turning points. Okay, so looking at this, where is our graph constant? That would mean that's asking where is it flat. This graph is never flat, so this is never constant. Okay, now where is our graph going up? From here to here, and then from here to here. Now remember, when we list these, it's always an open interval, and we're talking about on the x-axis. We're locating it. So this goes down forever. So this is from negative infinity up to my x value right here is -3. And then it's increasing again from this x value, which is -0.5, up to this x value, which is 2. It is decreasing from here to here, which is from -3 to -0.5. And then it's decreasing again from here to here, which is from 2 on the x-axis to infinity. Okay, now relative maxima, minima, and turning points. We have 2 of these, 2 points that are higher than everything else in their immediate vicinity, which are these 2 points. So I have -3, 4, and 2, 5. And at each of these 2 points, our graph goes from increasing to decreasing. So both of these are turning points. We have one relative minimum, which is right here. It is lower than everything in its immediate vicinity. So that would be at -0.5, -2. And it changes from decreasing to increasing, so it is also a turning point. I don't think you're going to find those problems too difficult. It is just a matter of remembering your notation. Okay. Another important concept when it comes to dealing with functions are even and odd functions. A function is called an even function if, for each x in the domain of f, -x is also in the domain of f, and if you plug in -x instead of x, you get the same answer. Okay? I tend to say, and this is my own personal way of expressing this, is that even functions absorb negatives. It just makes them all go away. Okay? The graph of an even function is symmetric with respect to the y-axis. And if you look down here at the example graphs I have given, this right here, if you fold on the y-axis, things would match up. This would be an even function. Okay. A function f is called an odd function if, for every x in the domain of f, -x is also in the domain of f, so that part is the same. And if you plug in -x instead of x, it puts a negative in front of the whole thing. So up here, the negative goes away. With an odd function, the negative goes in the front. Okay. The graph of an odd function is symmetric with respect to the origin. And what we mean by respect to the origin, this is an example of an odd function. And basically, it symmetry with respect to the origin kind of involves imagining two folds. If I were to fold this graph along the x-axis and then over the y, these should match up. So whatever is right here needs to be down here in a mirror image. Then the last option is that you don't have, what you have doesn't match either of these possibilities. For example, this is the graph we used on the previous page. It is not symmetric about the x-axis, the y-axis. If I fold it, they don't match up. And then, if I fold it here and then fold it here, it also doesn't match up. So this one is neither. It will be very useful later on to be able to look at a graph or an equation where we're going in a minute and to know whether you are dealing with an even or an odd function or neither, because these will be, in a lot of cases, relatively easy to determine what you have, and it can help you get your graph very quickly.